learned so many things, and I'm very thankful to, especially to Pablo and to the rest of the organizers, also to my good friend Marcelo and to Maria and everyone for having me here. This is not my area of research, and I'm here actually to learn. So this is very exciting for me because what I really do, what's my main area of research, is to study metal insulator transitions and transport in strongly correlated systems with disorder. And my main interest, one of the reasons why I'm very excited about this field is because this kind of area is where it turns out it's very important to understand the transport properties of materials even before you decide to build devices like memristors. And what I'll be doing today, I will not give a broad overview like Gergely. I will focus actually on something very specific that we have done very recently to address this question. And I'll try to be as brief as possible. First of all, we don't have much time. Second, I don't think that many people are interested in the mathematical details of what we've done. So I would like to highlight the ideas and skip the details and give you the main idea, the focus, why I think what we've discovered will hopefully be useful for memristors, but it will also indicate how my main line of work will fit in and how it's important to tweak the properties of materials in order to build useful devices. So, Gergely. Okay, so, but before I go on, let me just say that I'm also delighted to be here because this town is actually, I come originally from Serbia, from Belgrade, and as you can see, these two pictures, one is the Buenos Aires, the other one is in Belgrade. many streets actually look indistinguishable. So I truly feel at home here, and not because of the friendly people here, but also it just seems like some of the streets, I feel like I'm back home in Belgrade. I've been away from Belgrade for many years now. I'm actually working at the Florida State University in Tallahassee, also at the Magnet Lab, and I've been there for 30 years. I spent more than half of my life in the US, but I still feel nostalgia for beautiful cities like Buenos Aires and Belgrade. So let's go forward. So we heard a lot already about, and where's the, this is the projector. We heard already a lot of things about these devices that are so fascinating, and one of my main fascinations is that it's made often with transition metal oxides, and those are materials that are neither good insulators like silicon or good metals like silver. That's something in between, and it's an interesting area because I'm a theorist, and many body theory of that is difficult to actually understand, and especially the effects of impurities, and this is one of my main interests. Especially because when we look actually at we already seen this picture 3 or 4 times, you see that it's very granular, so these are very inhomogeneous systems. So you really have to, most of the people who develop theories for correlated systems, and I actually come from the same background as Marcelo, we were both in the Kotler group many years ago, and we continue working on correlated systems. Most of them focused on uniform systems, and rather recently people started to deal with inhomogeneities in correlated systems. So this obviously an exciting area, and then we've also seen some very interesting IV characteristics here which gives you rather impressive switching. And I'll come back to these pictures and tell you what are the features that I would like to actually focus on and try to understand it in a simple way. I'm telling Gergely to go forward. Okay, so these slides we've also seen, and it just shows that we have to form these filaments, and then this kind of physics is not so easy to understand. And from what I understand from this meeting is there's a lot of controversy exactly what is the nature of these filaments, how these devices are really formed on the microscopic level. These are very important and very interesting questions. They are also largely experimental questions, and it's actually amazing how much you can learn about all this without talking about theory, and I don't think this is a theory issue. One really has to use powerful tools that we have today and learn about it. So I'm not going to speak about it further, but I want to focus on one particular model or mechanism that has been proposed and that seems to reproduce amazingly well the behavior of several of these devices, and that's the model that Marcelo Rosenberg and his colleagues proposed. This model you have already seen, and it's supposed to describe a single filament which has regions which are more resistive than the bulk. And there could be various reasons for this, but this is a phenomenological input to this model. And this kind of model, it is a model of vacancies moving left and right under electric fields, and there is a rule that's been used simply to say there is a given probability to jump left and right. In absence of an external voltage, you have equal probability to jump left or right. So it's simple diffusion. However, because there is a voltage difference between neighboring sites, that creates an electric field, and that electric field pushes the vacancies in a particular direction. And that's modeled in this exponential. We have a voltage drop, or the local resistance. And when you start turning the voltage back and forth in such a device, you start from uniform densities, and then a sort of a profile is found where most of the vacancies pile up in the bulk, and they come in and out of these so-called Schottky barriers, which are more highly resistant regions forward. And what you get is curves like this. But here, what's important to emphasize is that the local resistance in the bulk is much, much smaller than the resistance in these barriers. And this is typically a very realistic representation, I think, of the actual physics. And they've chosen a particular set of numbers that were in this paper, that this is 1,000 times more resistive than that. However, what's assumed is that the local resistance is actually proportional to the density of these oxygen vacancies. And that's a particular choice that's stimulated by some realistic considerations. But one of the questions that I would like to answer is, how does that particular choice, how sensitive are the results to this? And what if you have something else? Like, for example, if the resistivity went down with vacancies. And already yesterday in a beautiful talk, Maria found that we have found quite different physics. And so a question that I would like to address today is, how can that happen? What exactly is happening in these materials? Why is this so sensitive to the resistance dependence on the vacancies? Forward. And actually, in this slide, the way how I actually started this work, a couple of years ago, Marcelo was visiting our group in Florida, and I had a number of summer interns, which are high school kids, and what they give them typically is to take some of our codes or programs and to make Java animations where you can visualize the various processes in real time. And we actually, on our website, which you can reach by clicking here, and in fact, I'll show you at the end of the talk how you can get to our website. It's called Bad Metals. You can just click there and you can see how this happens in real time. This is a profile of densities, and over here it will show you the resistance as a function of voltage, and then you can choose either a triangular excitation signal or sinusoidal or something else, and you can change the number of vacancies, total number of vacancies, the ramping field, and the resistance of the bulk and the barriers. And all these parameters can be modified, and I played actually with this quite a bit, trying to kind of, as a hobby, understand what's going on in some more detail. Because these simulations have already been done, they already have shown largely the relevant behavior, but some of the details I think remain to be understood. And I've been playing with this for a while, and then when a new graduate student came who was not really versed yet in many-body theory, I told him he wanted to start a project, to warm-up project. I said, why don't we look into this? And we've done a little bit of work on this over the last 6 months or so, and I wanted to show you what we have found, which I think you may find interesting and maybe stimulating for your own work. So here is the real-time actually movie that shows how this Java applet works, but you can, on the website, you can actually run it on your own computer and play with this. And I've actually played with this. What's interesting that you can change this time delay here, so you can move it slower in time or faster, and it's actually pretty interesting because it's much easier to watch what's happening in real time than to run a code and make plots, and that's a much more time-consuming process. And one of the challenges in this particular line of work is, and I think Marcelo and some students have already done some of it in quite an impressive fashion. The question is, if you change parameters, how is the behavior going to change? And you can explore this, you can run a code for different parameters, and that's a lengthy process with these Java applets. You can quickly do it. And I actually have these Java applets for many other areas of research that I work on. So we can go forward from here. There's one feature which is actually very easy to understand in this field. As I told you, the bulk has a lot of vacancies here. Most of the vacancies, after you train the device by switching the field back and forth, most of the vacancies find themselves in the bulk. And why is that? When these kids came, the high school kids came and they said, what's going on? Why do you have these, this looks like some sort of horns? Note that this is actually a logarithmic scale. So the density of vacancies next to this interface, just outside the Schottky barrier, is very high, and they pile up here. I said, well, kids, it's very easy to understand that. It's like the water slide. There is a force here on the water slide, pulls you down, and then once you drop into this pool, there is no more force. And if you have a lot of kids, which is, by the way, in the US now, it's forbidden to do that. There is a guard on the top of the pool, and the guard will not let the child jump down before the other child leaves the relevant area. So there is no pile up, because if they hit each other and break their head, they can be sued, and then hell will break loose. But you see, this is exactly what happens here, because the resistance here is larger in these Schottky barriers. So the internal electric field is very strong, and it pulls the vacancies away from the Schottky barriers. Once they arrive at this bulk region, then here the resistance is small, and the local electric field, the voltage drop across a cell is very weak, and they basically don't move much. And that, coupled with the fact that the total number of vacancies here is huge compared to those in the barriers, means that this is actually, for the theory point of view, a blessing. Because you can think of this bulk indeed as a pool. It's a reservoir where vacancies come in and out, but the process of these guys coming in and coming out is really fairly decoupled from the other ones, other than the fact that the total voltage drop is fixed. So the voltage drop can be either here or here, but not at the same time. Other than that, the individual diffusion through this barrier is really decoupled in these two interfaces. And so you can focus on one interface, dynamics of vacancies through this interface. And I think this is also very significant from the point of view of technology. Why? Because we know if we had to move these vacancies across the entire device, that would be extremely slow. These typically barriers are, as we've heard, on the nanometer scale, 10s or 20, 30 nanometers. And if you move the vacancies by a few nanometers, that can be a fast process. And and if that can make a huge difference, then we can make a fast device. So this is more or less what is happening here. And but we would like to understand exactly the dynamics. And so these curves that Marcelo and his collaborators published in that paper shows different values for the voltage. And this inset shows how the resistance changes. So initially, over here, most of the vacancies are piled up on the left. They start moving to the right. The resistance for a while is completely constant, which is sort of weird. It doesn't change at all. Then there's a very abrupt, sudden drop. And then, basically, by this time here, most of them have left the left Schottky barrier. And then they start migrating to the right Schottky barrier, resistance goes back up. And then if you reverse the voltage, again, it stays constant pretty much. Okay. So there are, the details of this will depend on the geometry of your device and on your protocol. It will depend on how the field is cranked up back and forth as a function of time. But some of the features are very robust and are universal. And this is what I want to focus on. So next slide. So these are the open questions that are the one that has interested me most is when you look at IV curves like this for this device, compare it to some other ones like the titanium oxide device from Hewlett-Packard. An outstanding feature here is that as you are ramping the voltage, there is a particular point where there's a very sharp drop. Actually, by changing parameters, you can make that drop even sharper. It's very sharp, and more or less, how sharp it is determines how deep you go, basically, how sudden is the switching. So I wanted to mostly understand why is this so sharp here? What's the reason for this? You can play with this, but already, in fact, Marcelo already had a good feeling about this, that as it happens, as these vacancies are moving to the right, they don't move, when you think about normal diffusion, you think that particles like to spread out and make some very smooth profile. You wait longer, they spread out more. Of course, we have a drift force that is pushing them, but you don't generally expect some very sharp features. Here we see that there is some very sharp drop here of the density. This is the density on the node on the log scale. So this here is about 10 times lower than that. there's a sharp drop, and then this front seems to move. And you may ask, well, what's causing this, and why doesn't it happen in the other device that Maria studied and displayed yesterday? So these are some of the questions. And so how steep this is? Why is it so sudden? And then, of course, it takes some time for these vacancies to leave. What is the time scale for that? And that's a question also related to the issue, as it turns out, and you've seen on the previous slides, this on and off resistance ratio deteriorates over time. And why does it happen? In this case, in this device, it happens, they come in and out, but the numbers of vacancies that make it back, so these come in and these then they come here, then they return. Every time this happens, fewer and fewer vacancies make it back to the Schottky barriers. So you're losing some vacancies, some of them are stuck in the bulk. And why is that? What determines that decay time? That's technologically also very important, because you want your performance to last for a long time. How can you prevent it? What is causing this loss? And in particular, for me, the most relevant question for my main line of research is if you change material properties of these, for example, this transition metal oxide. That will change how the resistance exactly depends on the concentration, local concentration. Can we understand that? One of the materials here is YBCO. This is a high-intensity cuprates that have people, theorists and experimentalists, are breaking their heads for more than 20 years trying to understand this. So these are the materials where we really do not have a good understanding how transport mechanisms, which transport mechanisms dominate, exactly what's causing the resistivity to go up and down. There is a lot of controversy even today. So I think this is a challenging open problem, but work in this area will be of relevance over here as well. So these are the questions that I want to focus on. And now I want to start telling you some of the work we've done. You may call it theory, and it's a rather trivial theory. In the theory, in the sense that one of my goals was that when I opened semiconductor physics books, you see some formulas. You know, for normal Schottky barriers, for p-n junctions, they're simple formulas. Even though my wife used to be a postdoc in IBM, they have codes to calculate everything in numerical detail. But if you have simple formulas that work in some simple limits, it gives you good guidance. You can guess what happens, and then you can try, even before you do massive simulations. The problem here is that simulations will be even more difficult because we don't understand the materials too well. So in semiconductor physics, they knew how silicon works, what's the effective mass of silicon, and everything. So, you could really do ab initio simulations very accurately. Here, to do ab initio work on transitional metal oxides, that's very challenging. And so I thought that if we can derive some simple analytical formulas to qualitatively understand the behavior of this model, I don't want to explain every model. There are too many, and this is a controversial area. But here is one model that seems to have a lot of relevant physics. I want to understand that model in a simple way, derive maybe a few formulas, and if we can do this, maybe that will give us some guidance where to go next, what else to try, right? So that is our goal. It's a simple type of theory that we want to do. And a lot of this work that I'll describe has been done by a new student, Xiao Tang, who is, I think, in my opinion, a genius. That only means that probably smarter than I am. Yes, so that probably means not that much, but it means much to me. So here's the model of Marcel and his friends again. There's a probability to move left and right. There's a prefactor, which they called Arrhenius factor, but it doesn't matter. It's just a constant that tells you a probability to jump back and forth. And then this is the concentration of vacancies. So the more vacancies you have here, the more probable will be to increase the density over here. And then you have a voltage drop in the exponent. So the idea here is, well, let's go to the continuum limit, and then we can write down, instead of this discrete master equation, we can write down a diffusion equation starting from this model. And how can we do this? Well, this is well known and it's easy. The current that flows from A to B, or from X to X plus dx, is just the probability to move to the right minus the probability to move backwards. Right? That's a simple step. And then you can write down these probabilities. They are given by this formula. If we just expand all quantities in dx, like this, so you have the density and this derivative, special derivative here, also you expand this term, the voltage drop, and this is just proportional, it is equal to the space derivative of the voltage drop. This is basically current times the local resistance, and in this model the local resistance is this prefactor A that tells you what material. Do you have a question? Yeah, well, you know, I actually can tell something about this. This term is a totally ad hoc term, first of all. If you have normal diffusion, this term doesn't exist. If you have uncorrelated random walkers, it will describe the fact that you have maybe a grain in which you can fit only so many vacancies. So if you have grains which can accommodate only 5 or 10 vacancies, that's very important. We can easily add that term. I skipped it here just for simplicity. The formulas look simpler. Turns out that it actually adds another term in the equation that I'll show you. And we have actually been able, we consider this term, and for the device that parameters that have been studied in the paper, this actually correction is by 2 orders of magnitude small. So it really doesn't play any role in the simulation parameters they've used here. But it can be included, and what's very nice, I'll talk about that in a few minutes, that the results, our main results about that shock wave are really independent of that extra term. And so I'll thank you for asking that question. I have forgotten to mention this. So basically this voltage drop is just the current times this A is that tells you the resistance of the local region. And then it's proportional to the density of carriers. And that's very important because when you write, so as a result of this, you plug this here and you get a current. The first term is the special derivative of the density. That's the usual diffusion term. But there is this other term. And this other term in the entire Schottky barrier or in the entire bulk, this A is actually X independent, but it's proportional to the square of the local density. And that's a very significant term, as you will see now in a second. So remember this formula here that we have the gradient term, but we have also the current proportional to the density squared and not something else. What I want to emphasize, if you had a force, drift force, or the local resistance, which was independent of the density of vacancies, that would be a linear term. And that makes a huge difference, as it turns out. So if you actually now take the continuity equation, number of particles is conserved, and you just take the derivative of the current, you arrive at this beautiful equation. This, by the way, has some coefficients have been rescaled here, so don't pay attention to that. But the important thing is that this, without this term here, that would be a simple diffusion equation. And we know everything about diffusion. We have a wave, the wave spreads out, and we know the width, how the width depends on time. So that's very simple. If we had a normal force, drift force, which would be independent of concentration, then there would be no U here. So a normal diffusion plus drift would give you a linear diffusion equation, and that also is easy to understand and not particularly interesting. However, when you have this nonlinear term, suddenly this is a nonlinear partial differential equation, which is known as the Burger's equation. This Burger's equation has been studied in actually several areas of physics, and it has some really remarkable and striking properties that I would like to describe to you. This has been discovered, and remarkably, you know, a lot of the differential equations that we learn in school and calculus has been discovered in the 18th and 19th century. This is not the case for these nonlinear equations. And nonlinear physics has really evolved in the 20th century, partly because they were able to confirm this and study further by computer simulations. And Johannes Burgers here actually died relatively recently. So he lived in the 20th century. He is the one who realized that this equation has a highly non-trivial solution and really studied the stability of this solution with respect to initial conditions, changing of the nonlinearity forms, and other things like that. So what he realized is that, in fact, I think some of it has been done, but I don't know the history too well. The remarkable thing here is that there is a transformation here called the Cole-Hopf transformation, which is given by this formula. And then if you plug U here, then this phi describes, obeys a standard diffusion equation. So now the standard diffusion equation, you can write down the solution through Green's functions in closed form for arbitrary initial conditions. And by doing this, Here is the actual closed form solution. Look at this. It's a complicated thing, but you can do this integral numerically or solve it in the long time limit analytically. And it gives you a solution. Now, I want to mention once more that if this is just a linear term, this is exact. If this is, say, u to a power 1.2 or 0.9, this result would not hold. However, there is another approach in mathematics which is called the method of characteristics, and which I'm not going to describe here, but that method can be applied very generally to nonlinear equations, and you can show by using this method that the criteria for forming shock waves are not dependent in detail on the form of this nonlinearity. You need to have a nonlinearity of a certain form, and then it's very generally true. So what you can actually show is this prefactor is a positive, it's an increasing function of u. Then you will always form shock waves. So it just has to go up with you. And now I would like to tell you about the physics. Why is that? How is that plausibly? What's the reason for this? Next slide. So here is the an animation which shows what happens if you start with a normal profile and let it run. And as you can see, we started with something smooth, and it immediately becomes very sharp. Look how this almost vertical thing is moving, and it's just moving and slowing down a little bit, and then it hits the edge. So this actually describes a very well-defined wavefront, and the remarkable thing is that the long time limit of that does not depend at all on the initial conditions. The shape of the wave initially is irrelevant, right? And it forgets initial conditions, and that's very useful because then you can basically, you don't have to worry exactly what happens at the beginning. At the end, it will form this shock wave. Why does it happen? It happens because this term says that there is a drift force which is proportional to density. So what does that do? If you have a wave like this, it pulls the top of the wave harder than the bottom of the wave, right? And just like you've seen those ocean waves, it tries to topple over. However, because of the diffusive term, that is arrested, and it forms a steady state solution. So what's necessary for this is that the force on the top of the wave is stronger than the bottom of the wave. And this is actually something not uncommon. For example, if you have differential rotation in the atmosphere of Saturn, the middle rotates faster than the edges, and you have this differential, that's why you have these rings of Saturn. And such things in hydrodynamics, when you have a lamellar flow also, and so for turbulence is a result of that as well. That you are pulling, that one section of the wave is moving faster than another, and that under these conditions, it creates this shock wave. So this is, you see, this is, when you see it with your eyes, it's extremely appealing, and you can see it, but it is a very robust feature of this equation. Next slide. I just wanted to mention, out of curiosity, it's interesting that exactly the same equation, in this case, that's a 1D equation, but there is a 3D generalization describing the velocity diffusion of gas. Jakub Zeldovich, in 1970, who was a genius, he was interested in astrophysics, and he was interested in the question in the universe initially there was a lot of gas uniformly spread out, but because of self-gravity, it tends to bunch up. And it forms something that is called today a cosmic web. So you see how these sharp features, these lighter regions are higher density than the lower regions. So this is a 3D version of this shock wave, and it shows that there are regions in space which are, and let's run it again, Gergely. So you can see how it bunches up and it forms these structures. Once the density, at some points where these filaments intersect, there's a very high density of matter. High enough density will start to condense into stars, and the intersection of these filaments are galactic superclusters. Okay. So this structure has been predicted by Zeldovich in 1970. In the last 20 years, this has been actually observed through deep sky Hubble experiments, and now there are many groups of people in the world who are studying the cosmic web. And actually, my son, who is now a college student, he wants to do his research in this field, and so I know a little bit about it. But it's a fascinating example how the same equation actually describes somehow very sharp features in the density distribution in many other areas of physics. And I'm not going to give you there are some other examples in biophysics and in other areas. But the point is, the reason why this is so important is because it's a very robust mechanism and it survives all kinds of details when you apply it to some different problems. Next slide. So now we can ask, well, how does it apply in our case here? Well, if you look actually at this formula, at this picture, you see here there's a lot of density here, but the resistance is very low. There are a few particles here, and there are lots of particles here in this left barrier. Now, because the local resistance of the left barrier is really high, that creates a huge resistance here. So the total resistance is dominated by that barrier, which is full of vacancies. And now we can write down what is the total resistance. Is just the local resistance is A times U. So you just integrate from 0 to the edge of the barrier. But note that if this shock wave is like this, so there's very few vacancies as a background. Most of them are in this section on the left of the shock wave. And as the shock wave moves, you've seen the animation showing you how it moves. Then this total resistance, it doesn't change at all for a while. Now, you can be more formal and you can take the derivative of this, but when you take the derivative of the density, continuity tells you that this is equal to the current derivative. Here, this is actually, I'm sorry, this should be x derivative. This is a typo. But because it's an x derivative, it kills the integral, and it tells you that the total derivative of this resistance is simply the current through the interface. Well, you'll say, oh, I could have guessed this, and you're right. Next slide. So this is very plausible, and it's just a formal way to do it. Now let's see how it applies to this device. So here, remember, I wanted to remind you that that the current is expressed only in terms of the first the special derivative of the density and the density square term here. Now the shock wave looks like this. There is a high density here and a very small or zero density here, and a sharp wavefront. And then when you actually, before it hits this interface, you want to evaluate the current through the interface, and that's because this shock wave is so flat here, then basically it's so flat here that you can ignore this term, and the derivative of the resistance or the resistance change with time or voltage is just proportional to density of vacancies on the right of the shock wave. And that's something very small, so the resistance doesn't change. Because most of the particles are left of the shock wave, and as the shock wave moves, it doesn't, very few actually go through. This is exactly what is actually happening in this simulation. And now, once the shock wave hits the barrier, suddenly the density jumps from U plus to U minus, which is much higher, and then the time derivative, the dRdV, is suddenly a larger negative number, and that tells you that the resistance as a function of voltage has a jump in the first derivative. And this the size of this jump, or the sharpness of this kink, is given by simply, here's the formula: diffusion constant, current, and here is the resistivity of the Schottky barrier, and the density of particles squared. And now we know the total number of particles here in the barrier. That's the maximum. The maximum resistance tells us what it is. And so we can basically, if we know the total maximum on switching resistance, we can calculate the discontinuity in the slope. So this is already telling us why this is so sharp. So probably the most important message from this work is that we have a very good understanding how suddenly in the middle of the voltage cycle can there be a jump or a kink in the resistance. It's because this sharp feature, the shock wave, hits the interface. If you didn't have this nonlinearity, and if you had normal diffusion, everything will be smooth and gradual, and that's what you see in some other cases. Next slide. So we have also some other results, and I didn't want to bother you with too many details. For example, you can calculate how the position of the shock wave front depends on time. You can actually write down some lengthy formulas. And how you can do these calculations, it's not so difficult. Probably any graduate student can sit down and figure it out. Also, you can use those formulas already existing. So let me just give you some results here. And what are the main results? That the front of shock wave doesn't move. It moves, its position is proportional to time at long times to the power 1/2. So the velocity actually goes as 1 over square root of time. So the shock, and you've seen this in the simulation, the shock wave starts and then it kind of slows down. But it doesn't completely stop, right, when it hits the barrier. It just slows down. And why is that important for me? Well, you know, it's important. You want to know the time it will take to, or what is the voltage you need to switch. I should be actually be a little bit more precise here because I'm switching between time and voltage. In their protocol, they had the voltage very linearly with time. However, if I had a different signal, if I had a square signal, so I keep the voltage on, constant voltage, then I switch it, and I switch it in the opposite direction, keep it constant, the shock wave would still be moving, right? And then the switching will not be as a function of voltage. I think it's better to plot it as a function of time. Of course, you know, you cannot do this in an experiment because this is at high frequency, but I just want you to keep in mind that this is actually a dynamical phenomenon. And the result, therefore, will depend on your voltage switching protocol. So you have to keep this in your mind. So there is a delay. The point is that there is a delay before I reverse the voltage here, I apply positive voltage, and there's a delay until it hits this barrier. And you can see this delay here. Here the voltage varies linearly with time. What? Gergely is sleeping. What is happening? The shock wave has hit. What has happened? I'm sorry. Okay. Maybe the contact got switched off. Let me just check a second. What is happening? Maybe they lost the contact. Gergely, check the contact. Maybe this here. Yeah, this contact. Sorry, it was the contact, yes. Okay, so there is a little delay here, and this delay will tell us 5 minutes. Okay, I'll be done soon. It tells the delay. Also, the height of the shock wave decreases, and that tells you that if I make the barrier bigger, okay, then the switching will be less sudden, for example. So you can get all this information. See, this is extremely simple. It's really not complicated. Next slide. Okay, so here are my conclusions. I have just this slide and another one. So the most important conclusion is that the sharp resistance switching is due to the formation of this shock wave. I told you that this is a very general phenomenon, and I think it is a very convincing because we have a simulation. We see this happening. We can understand all features of the simulation, but we know what will happen even for other parameters than those that have been studied in this particular paper. And for example, thinner Schottky barriers should give you larger resistance switching and faster switching. That's a useful piece of information. One interesting question here that I want to discuss in the remaining few minutes is this. If we had a different formula, how the local resistance depended on the concentration, not linear model. Let's say you had another power or something. Well, would this be completely wrong then? According to this exact solution called Hopf transform, it's valid for the linear form. Does it mean we know nothing? Absolutely not. As I mentioned, because of the method of characteristics, we know the qualitative form of the solution in general. And therefore, if I had another model of the local resistance, this prefactor could be any function of u. And what we prove here is that as long as this is an increasing function of u, exactly the same shock wave will form in the same way. So this is completely robust phenomenon because we cannot really be sure that the resistance is linear with concentration. That obviously is an oversimplified model. However, this phenomenon is completely insensitive to these details. But it's not totally insensitive because there are other barriers. We heard yesterday a very nice talk by Maria who said that in titanium oxide actually is the opposite. There's a different material, and there when you, because undoped titanium oxide will be an insulator, when you add vacancies, you actually increase the conductance, and the resistance drops down. So then this function here will be decreasing. Now, what happens then for this equation? Well, we know the answer to that as well. What happens then is that you are pulling the bottom of the wave faster than the top of the wave. You can prove this formally, but that's a very appealing argument. Then the shock wave never forms. And indeed, in her simulation, she finds that there is no shock wave in that case, and you have a resistivity IV cycle which doesn't have any sharp features somewhere in the middle of the cycle. And this is a very simple explanation. Even though the model has the very similar Schottky barriers and so forth, vacancies do come in and out of them, but there is no sharp feature, and I think this is the reason of that. The fact that the shock wave will form for some models and not for others. And I think this is a big challenge for me and my own line of work, because we would like to not only give general arguments like this, I would like to build microscopical models and ab initio maybe calculations of how a strongly correlated material like YBCO or PCMO, how do they respond to impurities like vacancies. We have to gain some serious understanding, and then we'll know under which conditions this will happen and under which conditions it will not happen. But this work gives you a criteria what to look for and what questions to ask. Next, transparency. I mentioned that this is my main line of work. Our book recently came out. It is basically a series of review articles describing the state of the art in this field. It's already published. And if you really want to learn about my own personal work, you can just Google bad metals, and our website, which is extremely colorful thanks to these summer interns and has a lot of attracting features. You can actually get all the information about me, my research, my students, while we do our papers from this website. I invite you to go there, and an added feature is that it has a number of these Java applets, not only for this, but for Coulomb glasses, for striped glasses, for all kinds of different problems we are working on. You can go there and play with the simulations and have fun. So I'll stop right here, and I thank you very much for the attention.
Thank you very much.